Hello, folks. Welcome back to Chemistry 132B, and this is going to be lecture number 5, and we're making good progress. Let me just dive into it straight away by just kind of quickly recapping what we talked about so far. Lots of new things. The main thing that we have been trying to do is to kind of build a framework for dealing with wave functions. Wave functions are the things that we need to describe the electron when it's part of an atom. We concluded that the wave-like properties of this electron are very important, and therefore classical mechanics fails and quantum mechanics is needed. But in order to use that, we needed a new framework, a new mathematical framework. So we have been slowly laying that out over the past 2 weeks up till now. So, very briefly, what we have seen is that there is something that we call operators, okay? And this could be any operator. We have seen some examples of this: position operator, momentum operator, the energy operator. The energy operator, in fact, has a special name. It's called the Hamiltonian, okay? But the common feature of all of these is that in many cases, depending on the situation, I can find a set of functions that I call eigenfunctions of this particular operator. So an important concept that we have to be familiar with. So the other thing, of course, is that, my actual particle, in this case an electron, because that's what we're interested in as chemists, is described by psi of x or r, depending on how many dimensions you are considering the problem to be in. In this case, it's a one-dimensional problem, so just x is fine. This wave function is what describes the particle, okay? Now, this wave function does not have to be an eigenfunction of a given operator. Now, let's make this more specific. So let's call the operator the Hamiltonian, the operator for energy. So let's say this wave function is in general not necessarily an eigenfunction of the Hamiltonian, okay? So, but I can always write the wave function as a weighted sum of eigenfunctions of, in this case, the Hamiltonian, the energy operator, okay? So if we had the scenario where, this wave function happens to be equal to one of these wave functions, one of these eigenstates of the Hamiltonian, then, of course, then psi is an eigenfunction of the Hamiltonian. And that is h with a little hat, right? So basically, this is probably stating the obvious, but it's important to realize psi is the wave function of the particle. Phi is an eigenfunction of the Hamiltonian in this case, because we're considering the operator to be the Hamiltonian in this example. Okay, so if the wave function is equal to one of the eigenfunctions of Hamiltonian, of course, then it is an eigenfunction of the Hamiltonian. So why is that relevant? Well, because if that is the case, then we can write the wave function and now include its time argument. Okay, so x, t, both a function of space and time. And we can write that as this is little psi that is only dependent on the spatial coordinates, and then there's a temporal part to the function, and that is written as follows. This is what we saw last time. This is h bar. Okay, so exponent I times E, where E is the eigenvalue of h, which is the energy. So E is the energy, T is time, divided by h bar. Okay, so that's the argument of the exponent. So we have a beautiful separation of variables, so to speak. So we have the spatial part and we have the temporal part. Okay, so that's what we ended on last time. Now let's take this and kind of see what that means. Okay, what kind of implication, what kind of physical implications that has. Okay. So let me share the following. Okay, so there's the function again. Hopefully you can see it. Okay, there's a negative sign now. That's okay. So there's a negative sign here. That's the same as before. This negative sign is actually, it is important. This negative sign. So there should be a negative sign there. So this is the general expression of the wave function. Again, the spatial part and then the time part. I forgot to put the negative sign previously, but there should be a negative sign there. So apologies for that. And if this, if this function is an eigenfunction of the Hamiltonian, then this expression is valid. Okay, why do I say that? Because in general, it's not necessarily so. Okay, so this expression is only truly valid if the function is an eigenfunction of the Hamiltonian, okay, with eigenvalue E. So in that case, what we have, and just to make sure that everybody understands how to expand this exponent, okay, this is a very important formula, of course. This is complex calculus, and we'll get back to it in a little bit more detail on Friday, okay? And I think some of you have practiced this already in the discussion sections. But we can write this complex exponent in terms of the cosine, which is the real part, and then the imaginary part, that is the sine. The same argument, E times T over H bar. Okay, so we'll be diving into this a little bit more deeply on Friday. For now, let's try to develop a physical picture of this. So what does it mean? So here's the wave function, and I'm writing now the spatial part. That's just like little psi x, and I'm putting this wave function, let's say, in this particular region between 0 and L, like we have done before. Let's say this is the wave function at a given time, okay, time t1. Now, the time evolution, of course, is given by the second part, okay, complex exponent. So a complex exponent, you see, it has these oscillatory functions, okay? So if I just look at the real part of this, that means at the later time t, it basically has a different value because, it oscillates like a cosine. So what does that mean? That means that this function at the later time could look something like this, all right? So at the later time, t2, it could have an opposite sign because the cosine varies between 1 and -1. So let's say the cosine has reached the value of -1, then my wave function will look like so. It's basically inverting. And at a later time, it goes back to t1, the t1 type of shape of the wave function. So it basically oscillates as a function of time. So the amplitude of the wave function is oscillating as a function of time between these two extremities, right? Within these bounds, the oscillation is going to take place. But we also know that if you want to look at the probability of finding the particle that is described by this wave function, we have to take the square modulus of this thing. Okay, and that's what we saw last time. If you do that, then this complex exponent, the square modulus of this complex exponent, equals 1, which is very easy to prove, and we'll do that on Friday in case you haven't seen it yet. And so what we're left with is only the complex, modulus square of the spatial part, and that's given over here. So the spatial part is plotted right here, and the time evolution of the probability, therefore, is constant. There is no time evolution, basically. It stays like this. Okay, so that's very important. So if my wave function is an eigenfunction of the Hamiltonian, then the probability density, this is called the probability density of the wave function, aka the particle, is just proportional to its spatial part and doesn't oscillate as a function of time. So it's constant. The probability distribution is constant in time, right? So it's time independent. The probability density is time independent. That's what it says. So that's good. So if my particle is in an eigenstate of the Hamiltonian, then my distribution in space, okay, as given over here, is remaining constant. Okay, the probability density of this particle is a constant in time and therefore is independent, time independent. No evolution. There's no evolution in time. It will stay where it is. Okay, so that's the kind of conclusion that we have. Now, but that's not generally the case, because we know that in general, the wave function could be a sum over eigenstates, right? And we have seen an example in one of the lectures that we have had. For instance, a sum over two possible states, eigenstates of the Hamiltonian. Now, if that is the case, then it's not necessarily time independent. You will see. Okay, so let's say psi1, little psi1 is an eigenfunction of the Hamiltonian with an eigenvalue of E1. Psi2 is also an eigenfunction of the Hamiltonian, but with a different eigenvalue, E2. Okay, so energy 1 for wave function psi1 or eigenstate psi1, and energy 2, a different value for the eigenfunction psi2. Okay, so the total wave function is a sum of each, of course, with weighing factors C1 and C2. Okay, and if I'm interested in the probability density, I have to take the square modulus of this entire thing. Okay, so this is the wave function with the time evolutions explicitly written out. Okay, so there is a time evolution. So there's a time evolution for the first part and a time evolution for the second part, for the second eigenstate. But because E1 and E2 can be different values, all right, these two time evolutions are not the same. And therefore, if I take this square modulus of the entire thing, there's going to be a cross term that is not going to be 1. In fact, it's not, and E2 are not equal to one another. In that case, you have a time argument that stays in this expression, okay? And that means that in general, the time evolution is not constant, okay? So it's not necessarily time independent. It's only time independent when the total wave function is an eigenfunction of the Hamiltonian. If it is a sum over several eigenstates of the Hamiltonian, then it's not necessarily time independent. It could be time independent, and especially in the case when this, the energies E1 and E2 and E3 and E4 are all the same, then it's still time independent. But if they are different, then it's not. Okay, so this is kind of an interesting conclusion. If the particle happens to be an eigenstate of the Hamiltonian, its probability density remains independent of time. But if the particle is described by a wave function that is a so-called sum or superposition of states, superposition of eigenstates of the Hamiltonian, then there is actual time evolution in my system. Okay, so the system will change its probability density as a function of time. Okay, that is a lot of stuff to think about. Okay, so let's now move on with some other important aspects of this wave function. So the capital psi, okay, that's what we have been looking at, is what defines the properties of my electron in the atom. So that's what we were indicating. Every time you see a capital psi, that's going to be the complete wave function of my electron. Okay. We also have seen that the probability density is written as psi squared, modulus square of psi. Now this density is basically, I should be a little bit more careful with my definitions here. Okay. This is called the probability density, modulus square of psi. This is basically a volume element. So a density times a volume element means that you integrate over space. And that implies that this is actually called, this total thing here is called the probability. That's called the probability. Okay, so that is one aspect that we are contending with, because this probability is a real thing. Okay, it's the probability of finding the particle in volume element dV. Okay, it's a real thing. So that's called the Born interpretation of the wave function. So this is a physical observable. We can certainly say something about the location of the particle using this expression. What else do we know about the wave function besides the fact that this is a physical interpretation of what the wave function is? Well, it also should be a solution to the Schrödinger equation. Okay, this is typically how people find the shape and the mathematical expression of the wave function. We are solving the Schrödinger equation, and if we do that, we find the state of the particle in such a way that the whole function is going to be an eigenfunction of the Hamiltonian. This is what we want, because if it is, then the energy of the particle is well defined. So this is what we will do, okay? And this is what most people do in quantum mechanics. You want your wave function to be an eigenfunction of the Hamiltonian, because then the energy of the particle is well defined. If you don't do that, then you have, not complete information about the energy, but we want to know what the energy is of the particle. So what we have to do is to solve the Schrödinger equation of for this wave function in this particular scenario. Okay, so we want both of these things to be true. Okay, we want the probability density, that's a physical interpretation of the wave function, and we also want the wave function to fulfill the Schrödinger equation. Now these two conditions here, or the first one is not really a condition, it's an interpretation. The second one is a condition. We want this wave function to fulfill this condition. These two aspects impose certain properties on the wave function. Okay, so let's first consider this probability density interpretation. This one here. Okay, and what kind of implications does it have for the shape or the properties of the wave function? So the first property is that if this really means probability, okay, that means that you can only have one value for one particular location, because you cannot have a location in space and have two different probabilities. It makes no sense. That's unphysical. You can only have one probability for each point in space. Okay, so a wave function that's indicated by the graph over here is not physical. Okay, so we have to impose a condition on the shape of the wave function. Consequently, because of this Born interpretation of the wave function, the wave function cannot have more than one value in each location in space. Okay, so that means that the wave function must be single valued. So this picture here, if you see, cannot be true. It must not have properties like this. It must have only one value for each position in space. Okay, so it must be single valued. Another condition is this: if you have a situation where the wave function goes to infinity over a certain finite domain, okay, as you see over here. So for x, let's say, this wave function is approaching infinity, so it gets closer and closer to infinity. That is unphysical, because that means that the probability density, which means integrating over this area, is going to fly to infinity as well. Okay, you cannot have a probability that approaches infinity. That's unphysical. The probability must be a finite value. Okay, because if you find a particle somewhere, that's a finite value. You cannot go to infinity. There's no infinity chance of finding the particle somewhere. That's unphysical. So we must therefore demand that the wave function cannot be infinite. However, there's a small note here, okay, because the real relation is that the wave function cannot be infinite over a finite region in space. Why is that? Because if I make my region in space infinitely small, then the wave function in principle could go to infinite, but only for that infinitely small point, okay? You cannot stretch it out over a wider region in space. So there's this kind of very special exception to this rule. It can go to infinity, but only over an infinitely small portion of space. And we'll get to that point, because it has a very important mathematical expression that we will encounter. Okay, but in general, the wave function cannot be infinite over a finite region in space. Okay, and that's all because of this Born interpretation that you see up here. All right, what about this Schrödinger equation? Does it also impose limitations? The answer is yes, because look at the Hamiltonian. Hamiltonian is a second order derivative with respect to space. And if the wave function is to fulfill this Schrödinger equation, it must have a second order derivative. Because if the second order derivative doesn't exist, then it cannot fulfill the Schrödinger equation. Okay, so therefore, we must conclude several things. First of all, the wave function must be continuous. Must be continuous. Why? Because if it has a break like here, that means that its first order derivative is not defined. Okay, you cannot have a first order derivative if there is a break in the values at a given point. This is impossible. You are unable to determine the first order derivative in a case like this. So that is that's not really something that we allow. The other probability, the other thing that we cannot allow is something like this, where there is, in principle, you can determine a first order derivative, but you cannot have a continuous second order derivative. Okay, so that means that the slope must be continuous as well. And if it is continuous, I can at all instances I can determine a second order derivative. But if the slope is not continuous, I cannot determine a second order derivative, which is ill-defined at this particular point where the slope has a discontinuity. So both the values of the wave function must be continuous, as well as the slope of the wave function must be continuous. Those are conditions that the Schrödinger equation imposes on our wave function. Okay, so those are some conditions. Let's keep them in mind. And then finally, look at a particular case where we can solve the Schrödinger equation and find a form of the wave function that, that has meaning. All right. So let's go here. Okay, so let's solve the Schrödinger equation one dimension, find a form of the wave function that has meaning. Okay, so what we have to do, we'll take this the Schrödinger equation main part, which is the Hamiltonian, and we can write down its kinetic energy as follows. Okay, and then we also say, well, let's just make the potential energy 0. Okay, so there's no potential energy contribution to my problem. Okay, so that basically means that V of x is 0 everywhere. All right, so no potential energy contribution to my problem. And that means that the particle only has kinetic energy. So this is the kinetic energy operator right here. All right, so then what I have to do is I have to solve the Schrödinger equation. Here it is. That's the equation that I have to solve. So let's do that. Okay, so let's just fill it out. Here it is. Only kinetic energy contribution, as we just determined. That equals the energy times the wave function again. Okay. I'm going to take this constant here. I'm going to move it to the other end of the equation. Okay, just to clean up the left-hand side. So I only have a second order derivative term. And I'm going to put this constant on the right-hand side. I get this. That's the equation that I'm having. I'm going to now rename this thing over here, because all of these things are constants, right? 2m h bar squared, and even E, the energy, is a so-called eigenvalue. So that's a number, right? So this is basically a number, and I'm going to call this number k squared. Okay, so that really simplifies my differential equation. So this is the differential equation I have to solve. The second order derivative with respect to space, x, operating on the wave function must give me kind of like minus k squared, okay, times the wave function again. So that's my differential equation. Now this is a second order differential equation. It's actually not so hard to solve. So let's do that. All right, and let's first make sure that we understand what k is. So k squared, just make sure we have that written out. Specifically, that's my k squared, right? That's the definition of k squared, which means that k is the square root of that, right? So that's the square root 2m e h bar. So that's what k is. Now, the general solution to this differential equation is something that looks like this. Constant, a, arbitrary constant, times I, k, x. That is a solution, okay? If you don't believe it, put it in the differential equation, and you'll see that it fulfills it, all right? So that is definitely a solution to this equation. Again, a complex exponential, they are very important functions. So we can call it psi1. There's another one that is almost similar, but slightly different. Call it b, arbitrary constant, okay, times e minus ikx, right? So this looks very similar, but it has a negative sign, and this is also a solution of that equation. Okay, so in general, I can just say, okay, this is a general solution of the Schrödinger equation. I just add these two guys up. And this sum is also a solution of the Schrödinger equation. Why? Because these two k's, negative k and positive k, both give the same eigenvalue, okay? The same solution. So they are equivalent, and therefore I can simply add them up. And so the most general solution to this differential equation, this second order differential equation, is this wave function, a, which is a, just a constant. We don't know what it is yet. Okay, we can determine it if we have more information about the problem, but at this point we don't know what A is. We also don't know what B is. A and B need to be determined depending on the situation, depending on the so-called boundary conditions of the problem. If there's any additional piece of information about this differential equation, then I can use that to determine A and B. Okay, but for now we don't have that information, so we don't know what these values are. Okay, so what does this mean? Does it have any meaning? I see just two complex exponentials. How do I interpret this? Well, let's focus on this first part, okay, psi1, which is, of course, this guy. And I'm going to determine the momentum of this wave function, okay, of this solution. How do I determine the momentum? Well, the general expression is doing this, the expectation value of the momentum operator, okay? The expectation value of the momentum operator. That's how I find the momentum if my particle resides in psi1. Now, you can do that, and I encourage you to do that for yourself, all right? I'm not going to write it out, so you should try it at home. It's not so hard, just following the definitions. But what you'll find is, okay, and I can tell you how you should calculate it, of course. You can have this situation, that's what you have to solve. And you have to do this. Okay, 1 dx. That's what you have to solve. It looks terrible, but in fact, it's not so hard to calculate. The answer here is that you find k h bar. All right, that is a solution. That is the momentum of the particle if the particle has the wave function psi1. Okay, so what does it mean then? Well, what this is, if you assume that an electron has the wave function psi1, then this electron is moving through space with a momentum that has this value, k times h bar. Okay, that's what it means. Now, what if the particle is described not by psi1 but by psi2? Okay, what does that mean? Well, it's actually not so difficult. So the momentum, if the particle is in state psi2, looks, of course, like this. Okay. Calculate that thing. And what I find, if you do that, you'll find that that is minus k h bar, okay? So remember, psi2 is b times complex exponential with a minus sign. Okay, so this is also a momentum, k, with a magnitude k h bar, but it has a negative sign. That means the particle moves in the other direction. Okay, so if you think about this, oops, that's a very strange line. This is, let's say, the x dimension. If I have an electron, okay, it zips in this direction with a momentum k times h bar if this electron is described by psi1, okay? But if it is described by psi2, it goes with the same magnitude of momentum in the opposite direction, right? So that's how I can interpret the kind of whereabouts, the information, physical information about the electron, if it were to be described by psi1 or by psi2. Okay, but now we have kind of this general expression. What does that mean? So in general, I can say it is a sum of psi1 and psi2. Okay, so what does that mean? Well, you know, psi1 and psi2, of course, have these coefficients a and b. So depending on how much a and b are, it can move with a certain probability to the right and a certain probability to the left. Okay, and so you have kind of a mixture of the two. So the particle could be in a so-called combined state and move to the left and the right. So let's look at a kind of an extreme situation of that. I can, for instance, say that A is equal to B, okay? And then just write out what the shape of the wave function is. So if I do that, I find the following. Let's say A is equal to B, so A, and then this is the first contribution, and the second contribution. Okay, so this is psi1, and the second part is psi2. And I can actually rewrite this in the form of a cosine. Okay, so this is basically using the cosine rule for the complex exponential. Okay, hopefully you know that, and if not, again, I will write that out very nicely on Friday, just to make sure everybody understands. Okay, but this basically is how you can write a cosine in terms of complex exponentials. So the combination of these two wave functions gives me a result that looks like a cosine. And if I now ask myself, where is the electron? Now, what's the probability distribution of the electron? Which means I have to calculate the probability density. That's the square modulus of the wave function, the total wave function. Then what I find is the square of this thing, which is 4a squared cosine squared kx. Okay, what does that mean? Well, that looks like something that is wiggly in a function of space. Okay, so this is the probability, p as a function of x. So what I find is there's locations where the probability is high, and there's locations where the probability is low. So it looks like a standing wave. It looks like a standing wave. Why is that? Well, that is because the particle is described by kind of a wave that travels to the right and a wave that is traveling to the left with equal probabilities, equal weights, right? And that leads basically to a standing wave. If you have two waves that are counter-propagating, think about two waves in the water that are counter-propagating, they set up a so-called standing wave. And that means that there's a probability distribution in space. There's locations where the wave is high, locations where the resulting wave is low. And so you get a standing wave distribution in space, okay? All right, so that is just a quick example. But let me now move to a little bit more of a relevant scenario, because this is basically a particle that's moving in space freely. There's no potential barriers. There's nothing that this particle will encounter. So it's just floating in space, right? Which is nothing like the scenario that we have, because we have a particle that is part of an atom. And in an atom, there's all kinds of things that keep the electron at bay, right? There's actually a potential energy. So let's start by introducing the potential energy contribution. This is going to be a very important part. All right, so let's make some space. All right, so we are introducing now the effect of the potential barriers. And now we have the Hamiltonian, which of course still has the kinetic energy contribution. That is a second order derivative, right? But now it also has a potential energy contribution. This last part is no longer zero, right? So if I now have to solve the Schrödinger equation once again, let's try that, see what happens. Okay, so I'm going to put this whole thing in. write it out. See what we can do with this, right? So plus this potential energy contribution, that's the wave function, and that should give me a constant, which is the energy, times the wave function again. So this is what I have to solve. Looks pretty terrible, right? But I'm going to do the same trick as before. Okay, so I'm going to say, I'm going to first take this part, right? And I'm going to move that to the right-hand side. Okay, so the potential energy term, I'm going to move to the right-hand side because it's kind of linear. There's no differential in there. If I assume that this potential energy is some kind of constant of some sort, okay, then I can move it to the right. So that's what I'm going to do. So what I'm getting then is this second order differential is still on the left-hand side, but I'm going to put the potential energy contribution on the, sorry, there's no, on the right-hand side. It's looking like this, okay? And I'm going to make it a little easier for myself because I'm going to consider only potentials that are constant in space. Okay, so I'm going to say that's a constant V0. Okay, V0 is my potential. Somewhere in space there's a potential barrier of value V0, but it doesn't change as a function of space. Okay, so that's just to make it a little easier for myself to understand this problem. Okay, so if I do that, what I can do, the same thing as I did before, I'm going to move that constant, this constant again, should be a square there, to the right-hand side. All right, so what I'm getting is something that looks very similar. Looks now like so. Okay, with a negative sign. Oh, something happened here. Help. There. Okay, so that is my my result, and I can do the same thing as before. I'm going to again call this whole thing here, I'm going to call k squared. So the situation looks very similar to the situation before. But now, of course, k squared is something different because now it has this effect of the potential energy in there as well. Okay, so let's make that explicit. Let's make that explicit. K squared is now something slightly different. Okay, because now it is 2m e minus v0 h bar squared. That's what it is. But that's it. That's the only difference. Okay, the differential equation is still the same otherwise. So my general solution is still, you know, this a times e ikx plus b minus ikx. That's still a valid solution where k now is a new definition. The difference is that there is now a potential energy contribution in there. Now, what are the consequences of this? Well, there are some dramatic consequences, okay? Because you know, what you can see here is that if this V0 is going to be larger than E, or E is the total energy, right? Then this k squared is going to be negative. And that's problematic because if you take the square root of a negative number, of course, you get a complex number, right? So k can become complex. So let's see what that means. I'm going to now look at 3 scenarios. Scenario 1 is where this E minus V0 is larger than 0. Okay, in that case, k squared is larger than 0. And that means that my solutions still very much look like, you know, my solutions before, like the solutions that I had before. So this is a, you know, the scenario hasn't really changed. The only thing that has changed is the value of k could be a little different, but the general form is still the same as before, right? Scenario 2 is when E minus V0 is equal to 0. What does that mean? That means that the total energy, E, is equal to the potential energy. All right. So these two things cancel out. And in that case, k squared equals 0. And if k squared equals 0, what I have is that the wave function now is, something that looks like, let me do it like this. Is proportional to E plus minus ikx, where k is now 0. So that is going to be equal to 1, okay? Because if you make k 0, if there's a 0 in the complex exponent, then the value is going to be 1, okay? So then the value of the wave function is going to be 1. That's remarkable, very different. So what does that mean? We'll have a look in a few seconds. But first, let's look at the other extreme, where the potential energy is higher than the total energy in my system. Okay, that sounds really odd, but we'll give meaning to that. Okay, so E minus V0 is less than 0. In that case, k squared is less than 0. And that means that the expression above, at the top of the page, is going to be a negative value. What do I do with that? Well, what I can do, I can slightly rewrite it. I can say, V naught minus E, this thing is still positive. Okay, but if you do that, there's going to be a negative sign on that all the way here on the left. Okay, so because I'm, oops, oh man, what am I doing? This is situation 3. I said is that is minus 2m E, sorry, V naught minus E. So this thing is still positive. This whole thing is positive, okay, by definition, because V0 is now more than E. That means that it's still a positive number, but there's a negative number here. Okay, so I can define the positive number as k kappa squared. This is a kappa with a negative value in front of it. Okay, and that means that k, which is now the square root of this whole thing, can be written as I kappa. All right, I kappa. So what does that mean? That means if I'm writing my function, let's say psi1 is a particle moving to the right, right, which had the form of this. But if k is equal to I kappa, then my wave function will look like I times I kappa x equals minus kappa x. That's different because there's no complex number in the argument anymore. Okay, it's actually a decaying exponential, which is a very different kind of function. It's not an oscillating function anymore as a function of space. It's now a decaying function in space. So let's have a quick look at what that means before we conclude. Over here. All right, can you see this? Yes. Can you see the images on the screen? Yes. Okay, great. So here's the scenario. Let's say as a function of space x, I have at some point in space, I have a potential barrier which is constant, like this, V0, okay, V naught. That's my barrier. Now let's say I have now a wave function that is this guy, particle moving to the right with a momentum k times h bar, right? That's just psi1, the one we have seen before. Now, if it is in the area to the left, all the way to the left, it can move like, in an oscillatory motion, okay? That's the wave-like properties of the wave equation, of the wave function. But if it now hits this barrier, what happens is in case 1, when the energy, the total energy of the particle is still higher than V naught, then the wave function still looks the same. The only thing that has changed is the value of k, which is now a little less. If k is a little less, that means that the wiggling nature is slowed down a little bit, and therefore it still wiggles. It still is a wiggling wave function, but the number of wiggles as a function of space, or the number of wiggles over a certain length scale, is now going to be less because k has a lower quantity now, lower value. Okay, when it moves out of the barrier, it resorts back to its original shape, and therefore it starts wiggling on as before. Okay, so the only difference in the barrier now is that it wiggles less vigorously as a function of space because the value of k has been reduced. The higher k, the more wiggles over a certain length scale. The lower k, the fewer wiggles over a length scale. Okay, so that's basically scenario number one. The first case we have encountered when the total energy of the particle is more than the potential barrier. Now, scenario number two is when the energy of my particle is equal to the height of the potential barrier. Okay, so E is equal to V naught. The total energy of the particle is equal to the energy of the barrier. What did we find? The wave function now is 1. Okay, it's flat. It's flat inside the barrier. It doesn't wiggle. It has lost its wiggly character at all. Right, so it's a constant now, and it doesn't change as a function of space. When it moves out of the barrier, it actually continues on as before. All right, so also note that at the boundaries from, let's say, motion in free space to the barrier, the wave function must be continuous. Okay, so it must be continuous at the barrier. Same here and there. This is something we have required. This is a property of the wave function that we just required at the beginning of the lecture. Now, the situation of scenario number 3 is very different. Okay, so we have a particle that's moving to the right. When there's no barrier, it just is a wiggling function moving to the right. But if it hits the barrier, then and the barrier is higher than the total energy of the particle, then we found that the wave function is this decaying exponential. It's not a complex exponential, meaning it's not an oscillatory function. It is now a decaying function. So when it hits the barrier, the amplitude of the wave function is going down, right? When it wiggles out of the barrier, when it comes out of the barrier, it still has an oscillatory motion, oscillatory shape, but the amplitude is now much less. Okay, so it has lost its amplitude. And so this is a pretty dramatic situation. Okay, so the properties in the barrier are remarkable, especially in the case when the particle has not enough energy to overcome the potential energy. But, and this is very important, of course, you can see that the wave function doesn't go to 0 completely and abruptly. It's a decaying function, so the amplitude is decaying, decaying, decaying. The more it propagates into the barrier, but it's not 0. In fact, it will never reach 0 completely. Okay, it always has a finite value. So why is that so remarkable? Because think about a particle that is described by a classical in classical mechanics. Okay, if you have a particle like a tennis ball, and it has a certain energy, the total energy of the tennis ball, which is defined by its motion, let's say, and its potential energy. If I'm trying to have the tennis ball penetrate a barrier that is higher than the total energy, the tennis ball simply won't go there. Okay, it will bounce off the wall. That's a good analogy. A tennis ball, if you hit the tennis ball, if you hit the wall with a tennis ball, okay, and the energy of a tennis ball is less than the potential energy of the wall, then it simply won't go through. But here, you have a situation, in the case of the electron, where the electron actually is going to penetrate the wall. It's going to go into it, even though it doesn't have enough energy. And what we'll see is that the amplitude, the probability of finding the electron in the wall is progressively going down the more you penetrate into the wall, right? But it's still a scenario very different, or an outcome very different from the outcome you would expect based on classical mechanics. This property is called the tunneling of the particle, or the tunneling of the wave function into a barrier. A barrier where the particle is not allowed classically, but it is allowed quantum mechanically. All right, so that is kind of where we're going to start next time on Friday, where we will be considering some solutions of the Schrödinger equation with the inclusion of potential barriers. Okay, and we'll see that this is really relevant for the situation of the electron and the atom, because again, the atom is confined to the atom, so it experiences real potential barriers, real potentials that confine the particle to the atom. Okay, I'm going to leave it at that, and if you have any questions, please This is a good time.
Hello, can you hear me?
Yep.
Can you go back to the slide where we talked about kappa?
The slide where we talk about kappa. Okay, so that slide doesn't exist anymore because those are scribbles. Let's see. I can write kappa here. So kappa is, so basically here in the barrier, the wave function has this shape. Okay, so it's a decaying function. It's a function of space. So it goes down, the higher x, the lower the value of the wave function. Okay, now this kappa was defined through k squared. So k squared equals, the definition of k squared is this. Okay, E minus V naught. That's my definition. There should be a square right there. All right. And so, but what I'm saying here in this scenario number 3 is that V naught is larger than E. Okay, so I'm going to switch the order of these two guys. So when I do that, of course, that basically means I'm extracting a negative sign out of this argument between parentheses. Okay, so it's going to be a negative sign there. This factor is still there. Okay. So that means that k squared is a negative number for sure, because this whole thing is positive. It must be, because this is how I define it. V naught is larger than E for scenario number 3. Only for 3, of course, right? Not for scenario number 1. Only for 3. So in number 2, this kappa. So this is the definition of kappa. K squared equals negative kappa squared. And that means that if I take the square root of each side, that I have this kappa squared, and I can write that as I squared kappa squared square root, and that means -1 kappa, oh, not kappa squared, just kappa. Forget about this. Okay, so that's what kappa, how kappa is defined. That is the definition of kappa. All right, and so if I have this condition in the barrier, the wave function is defined as a constant times EIKX. Okay, but now K is complex. Okay, so that becomes E minus kappa X. And that's the function right here. Does that answer your question?
Yeah, thank you so much.
Mm-hmm.